Module 9, Lecture B, Serving and APIs. By the end of this lecture, you will be able to deploy a saved model using TensorFlow Serving or a similar serving stack, expose a prediction API endpoint that accepts JSON inputs and returns model outputs, and evaluate basic performance characteristics of a served model, including latency and throughput. TensorFlow Serving Basics. Dockerized TF Serving. Dockerized TensorFlow Serving means running TensorFlow Serving inside a container built from a pre-configured image that already includes all required components. This approach simplifies deployment by avoiding library conflicts and differences between systems. A data science team can train a model, export it as a saved model, and hand it off to engineers, who then run it in the same standardized container in any environment. As a result, the container becomes a consistent unit that provides reliable model serving from development through production. In a Dockerized setup, you mount the directory containing your saved model into the container and configure TensorFlow Serving to load the model from that location. The container then exposes a network port for prediction requests, so other services see it as a simple network endpoint without needing to know its internal details. This clear separation is important in organizations where data scientists and platform engineers have different responsibilities. Data scientists can retrain and save updated models to a shared location, while engineers adjust the containers to point to the new model path, ensuring the system reliably runs the latest version. Dockerized TensorFlow Serving integrates smoothly with orchestration tools like Kubernetes and Docker Swarm to provide robust, scalable model deployment. These platforms can automatically scale containers up or down based on traffic, restart them if they fail, and manage rolling out new versions of the serving image. For instance, a company running a fraud detection model can add more instances during peak usage to keep latency low, then gradually shift traffic to a new model version while monitoring its performance. This setup makes model serving a reliable and flexible part of production infrastructure. Managing model versions. Managing model versions is essential when moving from experimentation to production. In TensorFlow Serving, each model version is stored in its own numbered folder within a model directory. This structure lets you load, unload, and switch between versions without changing the serving system or client applications. For example, a recommendation system can host several versions of a model at once, while clients keep using the same model name. This approach allows the system to evolve over time without disrupting the applications that depend on it. In TensorFlow Serving, controlling which model versions are active is important for safe deployment. You can choose to load only the latest version or keep several versions in memory at once. This lets you send some traffic to a new model, compare its performance with the current one, and ensure it does not cause issues such as more false positives in fraud detection before making it the default. These versioning policies enable canary releases, A/B testing, and quick rollbacks, all while keeping the external endpoint stable for clients. Managing model versions requires planning how to use storage, memory, and compute resources over time. Each version takes space, and active versions also consume memory and processing power, so you need clear rules for which versions to keep loaded and which to retire. In sensitive areas like healthcare prediction, you may retain older versions for auditing, while limiting how many are active to control resource use. Monitoring should track which versions are running, how well they perform, and any issues that appear after a version change. Over time, you can automate promoting well-performing versions and retiring unused ones to maintain reliability and continuous improvement. When you deploy a model with a dedicated serving system, Clients communicate with it through serving API protocols such as REST over HTTP or gRPC. These protocols define how requests and responses are formatted and how errors are handled. The Serving API exposes endpoints that accept serialized inputs, route them to the correct model and version, and return predictions in a machine-readable form. Understanding these protocols is essential because they are the link between your model and any application or service that uses its predictions, from web backends to mobile apps and data pipelines. Serving API protocols for models are designed to be both flexible and strict. They can handle many kinds of model inputs, from simple numbers to complex data like text and images. But they require precise encoding and labeling so each request matches the model's expected inputs. If a client mislabels or leaves out a required field, such as a user or item identifier in a recommendation system, the server will return an error. This strictness ensures different teams and systems can integrate reliably without needing constant coordination. Serving API protocols do more than pass requests and responses. They also control important behaviors needed in real applications. They can batch multiple predictions in one call for efficiency and expose metadata so clients can discover model details and input requirements. In large organizations, many different models, such as fraud detection and language understanding, can share the same protocol, which makes it easier to build common tools and libraries. When you define model endpoints, you are choosing a stable protocol that other systems will depend on, so you must carefully design input and output names, required fields, and how the protocol will evolve over time. Python code. Serving API protocols. This script introduces the basics of serving API protocols by simulating prediction requests using both REST and gRPC styles. It focuses on how the requests are structured rather than on real network communication. The goal is to help you understand the typical shapes of these requests in a simple, controlled setting. The commented line with the pip install command is a note suggesting the installation of the TensorFlow Serving API, a library used to deploy machine learning models so they can provide predictions through REST or gRPC. Because the line is commented out, it indicates that installing this library is optional or may have been done already. This setup is important when running the script in environments where TensorFlow Serving is needed to handle incoming API requests for model predictions. We begin by importing 3 key libraries that prepare our script for working with data and computations. The JSON library lets us handle data in a common interchange format. The random library allows us to generate random numbers, which is useful for creating test data or simulating different scenarios. The numerical computing library, NumPy, provides efficient support for arrays and many mathematical operations. Together, these imports give us the basic tools we need for data handling and numerical processing in the rest of the script. We begin by setting fixed random seeds using the random and numerical libraries so that any random numbers they generate are the same every time the script runs. Using a specific seed value makes all random behavior predictable. This predictability is important for debugging and testing because it allows us to reproduce results consistently and verify that changes in the code are the real cause of any differences we observe. We begin by converting the batch of input features into a numeric array of floats so the data is in a consistent format. We then verify that this array is two-dimensional, since that shape is required for the matrix operations we will perform. A two-dimensional weight array with values 0.3 and 0.7 is defined and used to compute a score for each feature set through matrix multiplication, which combines the features linearly according to these weights. These scores are passed through the logistic function to turn them into probabilities between 0 and 1. Finally, we remove any extra dimensions so the probabilities form a simple one-dimensional array that is easier to work with later. This function builds a fake REST request body in JSON format. It first checks that the lists of user IDs, item IDs, and scores all have the same length, and raises an error if they do not, to keep the data consistent. It then loops through these lists together, and for each set of values, creates a dictionary with fields for user ID, item ID, and score, converting each to the correct type and adding it to a list of instances. After all instances are created, it wraps this list in a single dictionary under one key and converts the whole structure to a JSON string. That JSON string is returned as the body of the REST request. We begin by converting a JSON string into a Python dictionary and checking that it contains a required key called instances. From this key, we extract a list of instances and prepare an empty list to store feature sets. For each instance, we verify that it has the fields user ID, item ID, and score, and if any are missing, we raise an error that names the missing field. We then build a feature list from the user ID and item ID for each instance and add it to our collection. In the end, we return two NumPy arrays as floating point numbers, one containing the features from the last instance and one containing the features from the entire batch. This description explains a helper function that builds a fake gRPC-style request for a recommendation model. The function takes three lists of user IDs, item IDs, and scores, and first checks that all three lists are the same length, so each user has a matching item and score. It then creates a nested dictionary called Tensor that stores user IDs, item IDs, and scores along with their data types, converting the IDs to integers and the scores to floats. Finally, it wraps this tensor in another dictionary that includes the model name demo recommender and returns it, mimicking the structure of a real gRPC request. This function parses a gRPC-style request into model inputs by first confirming that the request includes an inputs field and raising an error if it does not. It then extracts the inputs and checks that the required entries for user identifier, item identifier, and score are present, again raising an error if any are missing. The user and item identifiers are converted to NumPy arrays of floats, and their shapes are compared to ensure they match. Finally, these two arrays are stacked along the second axis to create a batch of features which the function returns. We create a small batch of example features to test our dummy prediction model. We define user IDs with values 1, 2, and 3, and item IDs with values 10, 20, and 30. We also define scores with values 0.1, 0.5, and 0.9. Together, these lists simulate input data, so we can see how the model handles different user and item combinations along with their associated scores. We start by building a REST-style request body using a helper function that takes user IDs, item IDs, and scores and packages them into a JSON string. This JSON request is then parsed to pull out the features needed for the model. The parsing step checks that all required fields are present and converts the data into a suitable internal format. Finally, the data is organized into a two-dimensional NumPy array that represents a batch of features ready to be passed into the model for prediction. We first build a request in a gRPC style using a helper function that takes user IDs, item IDs, and scores, and organizes them into tensors with specified data types and values, all wrapped in a request dictionary that includes the model name. Then we parse this request with another function that checks for the required fields and converts the input values into NumPy arrays. This parsing step verifies that user and item IDs have matching shapes, and then stacks them into a two-dimensional array. The result is a clean set of features properly formatted and ready to be fed into the model. We run predictions with our dummy model using both REST and gRPC requests to show they lead to the same model behavior. First, we extract features from the REST request and pass them to the model's prediction function to get probability outputs. Then, we repeat this process with features extracted from the gRPC request. Comparing these results lets us confirm that both protocols are mapped to identical model inputs and produce consistent predictions. We first print the JSON version of the REST request to see the structure of the request body that was created. Then we print the predictions from this REST request, converting them to a list so they are easier to read. Next, we display the keys of the gRPC-style request to reveal its structure and verify that the expected fields are present, followed by printing its predictions in list form as well. This process highlights that although REST and gRPC use different request formats, they both ultimately provide the same underlying inputs to the model. This script shows how to simulate both REST and gRPC-style API requests for a simple prediction model. It first fixes the random seeds for reproducible results, then defines a basic model that applies a linear transformation to input features and converts the result to probabilities with a logistic function. The code builds a fake REST request as a JSON body with user and item information, and a gRPC-style request as a dictionary, then parses each into feature batches suitable for the model. It runs predictions on both types of requests and compares the outputs. The key result is that both REST and gRPC requests are converted into the same model inputs and produce consistent predictions, demonstrating equivalent behavior across the two API styles. Designing prediction APIs. JSON request design. When you design a request format for a prediction endpoint, you are creating a clear contract between your clients and the model. This format should specify exactly which inputs are required, such as feature values and metadata, and give each piece of information a clear name and type to prevent confusion. Whether the system sends customer and product data in retail or image references and patient details in healthcare, the structure should be explicit and consistent. The main goal is to make requests easy to validate and understand so different systems can integrate with the model smoothly. When designing model inputs, you need to balance what is convenient for clients with what works best for the serving system. Serving systems usually expect data grouped by feature names, while clients think in terms of single prediction requests. To connect these views, the service maps client-friendly request structures into the model's required tensor formats, such as turning transaction details into the shapes needed for fraud detection. By centering the API on domain concepts and hiding low-level details, you can keep the external interface stable, even as the internal implementation changes. When designing a request format for an API, it is important to plan for optional parameters, versioning, and future extensibility. Clients may need to specify things like how many results they want, a confidence threshold, or which model version to use, all in the same request. For example, a content moderation service might accept text along with a language hint and sensitivity level, and decide whether to return a simple decision or more detailed scores. By keeping optional fields clearly separate from core features, you maintain clarity and backward compatibility as the API evolves, leading to smoother integration and fewer issues when models change. Python code, JSON request design. This material introduces the basics of designing JSON requests by simulating a very small prediction API service. The main goal is to show how to structure JSON requests clearly and consistently. Rather than focusing on complex logic, it emphasizes clean, well-organized request formats. By the end, you should understand how to design simple JSON requests suitable for a prediction-style API. This script requires TensorFlow, but it is already installed in the environment, so you do not need to add any extra libraries. Because TensorFlow is pre-configured, you can run the code without worrying about setup steps. This allows you to focus directly on the main tasks the code is designed to perform. We begin by importing a library for working with JSON data, so we can create and read structured requests and responses. We also import a random number library to control random behavior, which lets us set fixed seeds and make our experiments reproducible. Finally, we load TensorFlow, a machine learning library that we will use to build and train a simple neural network as a demonstration. We set deterministic seeds for both the Python random module and TensorFlow, so that any random operations give the same results every time the code runs. Using the same seed value fixes the sequence of random numbers in Python and makes TensorFlow's random behavior, such as neural network weight initialization, consistent across runs. This reproducibility is crucial in machine learning because it allows us to reliably test, compare, and debug models under the same conditions. This line displays the version of TensorFlow currently in use. It helps you quickly confirm that TensorFlow is installed correctly and lets you know exactly which version is running. This information is important because different versions may behave differently, so knowing the version can help with compatibility checks and debugging issues. We build a simple neural network model using the Keras sequential API, which stacks layers in order. The model takes input data with 3 features, then passes it to a dense layer with 4 neurons that use the ReLU activation to add nonlinearity. After that, the output goes to a final dense layer with 1 neuron that uses the sigmoid activation. This last layer produces a value between 0 and 1, making the model suitable for binary classification tasks. The model is compiled with a simple setup that uses the Atom optimizer, which is widely used because it trains neural networks efficiently and adapts during learning. It also uses binary cross-entropy as the loss function, which is appropriate for binary classification problems. This loss helps the model quantify how different its predictions are from the actual target values, so it can improve during training. We begin by creating a small dummy dataset for training a model. The input features are defined as a constant tensor with 2 examples, each containing 3 float values. One example has values around 0.1 to 0.3, and the other has values around 0.7 to 0.9. We then define the target labels as another constant tensor, where the first input is labeled 0 and the second is labeled 1, both stored as float values. Together, these tensors form a simple input and output pair that we can use to train and test the model. The model is trained using a fit method that takes input features and their corresponding labels, which are the expected outputs. Training runs for 5 epochs, meaning the model goes through the entire dataset 5 times to adjust its weights and improve accuracy. The verbose setting is turned off so that no progress messages are shown during training. This makes the process run quietly and can be helpful for quick experiments when detailed training logs are not needed. We define a function called buildRequest that creates a JSON request body. It takes a required parameter called instances and an optional parameter called options. Inside the function, we first create a base request as a dictionary that has 1 key named instances. The value of this key is the instances data passed into the function, which ensures that the instances are included as a list in the final JSON request structure. When the options parameter is not empty, the code adds a configuration section to the request dictionary. This configuration section carries any extra settings or parameters needed for processing. Including these options makes the JSON request more flexible because it can adapt to different requirements without changing the basic structure of the request. This function creates a JSON string from a request object by converting a Python dictionary into JSON format. It uses a standard JSON library method to perform the conversion. The keys in the resulting JSON are sorted alphabetically, which helps keep the output consistent. This consistent ordering is useful when debugging or comparing different JSON outputs. The function starts by receiving a JSON formatted string as its input, which represents the request body. It then uses a JSON parsing tool to convert this string into a Python dictionary. This conversion organizes the data into a structured form, making it easier for the function to access, understand, and modify the information contained in the original JSON request. The code first verifies that the data dictionary contains a field named instances, and that this field is a list, because the function expects to process a list of instances. If either the field is missing or its value is not a list, the code raises a value error. The error message explains that the request must include a list field called instances. This validation step ensures the incoming JSON request has the correct structure before any further processing occurs. The code first extracts the instances entry from the parsed JSON data, which holds the input data points the model will use to make predictions. It then tries to read the configuration entry, but if that is missing, it falls back to an empty set of settings. This approach lets the function support optional configuration without causing errors. As a result, the request format is flexible while still providing the model with the inputs it needs. We create an empty list to hold feature values, then process each item in the collection of instances. For each item, we first confirm that it is a valid JSON object. If it is not, we stop and report an error. We then check that this object includes the required fields named F1, F2, and F3, and raise an error if any are missing. After an item passes these checks, we take the values of F1, F2, and F3 and add them as a small list to our main features list. By the end, we have a clean, structured list of feature values ready for later analysis or modeling. This line turns the list of features into a TensorFlow tensor with a data type of float32. This step is essential because TensorFlow models need data in tensor form to run their computations efficiently. By explicitly setting the data type, we make sure the model handles the input correctly and keeps the desired level of consistency and precision during predictions. This function returns two things: a features tensor and a configuration dictionary. The features tensor is a TensorFlow tensor built from the input data in the JSON request and is ready to be used for model predictions. The configuration dictionary contains any optional settings that were included in the JSON request. Together, they provide both the data needed for prediction and the settings that control how the prediction is made. The predict endpoint function simulates a prediction service by accepting a JSON formatted string as its input. This string represents the request body sent to the model. Inside the function, the request is first parsed and validated by a separate parse request function. That helper function processes the JSON and returns a tensor of features along with a configuration dictionary. This ensures the incoming data is correctly structured and ready for the model to use. The code first reads the maximum batch size from the configuration, using 16 as a default limit. This cap helps control memory use and processing time. It then checks whether the number of instances in the features tensor is larger than this limit. If so, it trims the tensor so it contains only up to the maximum number of instances, which keeps processing efficient and prevents overload when working with large datasets. The code calls the model's prediction function on the features tensor, sending the input data through the model's layers to produce output predictions. The verbosity setting is turned off, so this prediction step runs without showing any progress or status messages. This silent mode helps keep the output clean, which is especially useful when predictions are part of a larger automated process. The code builds a dictionary to store model predictions in a convenient format. It takes the first column of the predictions array, converts all its rows into a list, and places that list under a key named predictions in the dictionary. Organizing the data this way makes it straightforward to turn the predictions into a JSON response. This function returns a response as a JSON formatted string. It uses a JSON library to convert an internal response dictionary into this string representation. The dictionary's keys are sorted in alphabetical order before conversion so that the output format is consistent every time the function is called. We begin by creating a list of client instances where each item is a dictionary representing one data point for our prediction model. Each dictionary contains 3 numerical features called F1, F2, and F3, along with a user identifier stored as a string. This structure simulates real-world input to a prediction service, with each instance standing for a unique user and their associated feature values. In this setup, an optional configuration for the request is stored in a dictionary called the client configuration. It includes a setting that limits the maximum number of instances processed in a single batch to 4. Another setting turns off extra explanations or metadata in the response. Together, these options control how the prediction endpoint handles and formats incoming requests. The build request function creates a JSON request body for the prediction endpoint using 2 inputs, client instances and client configuration. Client instances are a list of data records, where each record includes features such as F1, F2, and F3, plus metadata like a user ID. The client configuration is a dictionary of options, for example, settings for maximum batch size or whether to include explanations. By combining these inputs, the function produces a structured JSON string that organizes the data so it is ready to be sent and processed by the prediction service. We send the previously built JSON request to a simulated prediction endpoint, which is designed to accept this input, parse it, and check that its structure is valid. After parsing, the function extracts the relevant data and passes it to a pre-trained model to generate predictions. These predictions are then packaged into a JSON response and returned to the caller. This entire flow mimics how a real prediction API would receive requests and produce responses. The script first prints the JSON request to the console so you can check that its structure and contents are correct before it is sent to the prediction endpoint. It then prints the JSON response returned by the endpoint. Seeing both the request and the response helps you verify that the model's predictions are being received properly, and that the overall request and response formats are consistent and correct. This script shows a simple prediction API built with TensorFlow that uses JSON to send and receive data. It defines a small neural network with 3 input features, a hidden layer with 4 nodes using a rectified linear activation, and a single output node with a sigmoid activation, trained briefly on dummy data with the atom optimizer and binary cross-entropy loss. The script includes helper functions to build JSON requests with instances and optional configuration, and to parse and validate those requests, checking that each instance has 3 required fields and converting them into a TensorFlow tensor. A prediction endpoint function then processes the JSON, applies any batch size limits, runs the model to generate predictions, and returns them in a JSON response. Finally, the script creates a sample request, sends it to the endpoint, and prints both the request and response to demonstrate the full client-server interaction for machine learning predictions. Service layer preprocessing. Between the prediction endpoint and the model, a service layer usually converts raw client data into the format the model expects. This is important because client data often comes in mixed types, while the model needs structured inputs such as token sequences or encoded categories. The service layer checks that all required fields are present, values are valid, and data is correctly turned into tensors or arrays. By centralizing this work, it keeps the model interface stable and predictable, even when client requirements change. A well-designed service layer makes sure that all feature engineering and normalization steps used during model training are applied in exactly the same way when the model is serving predictions. This includes operations like standardizing numbers, bucketing values, creating time-based features, loading lookup tables, and applying the same scaling and encoding used offline. If these transformations are not mirrored at serving time, the model may see inputs that differ from its training data, and its performance can degrade. In a recommendation system, the service layer can map identifiers to embeddings and assemble the final feature vector for the model, while keeping these details hidden from the API client. The service layer does more than transform data. It also enforces rate and size limits to protect the model, removes personal information, and fills in default values when needed. It is a central place for logging and metrics, which helps detect issues such as data drift. In domains like healthcare, it checks that inputs such as vital signs are within normal ranges and standardizes units from different sources. Overall, this layer acts as a boundary that keeps client data clean and meaningful so the model can focus on accurate and reliable predictions. Python code. Service layer preprocessing. This script demonstrates how to handle preprocessing in the service layer before making a model prediction. It works with a simple JSON-style prediction request and shows how such input might be received. The main goal is to clean and prepare the incoming data so it is in the right form for the model. By focusing on input cleaning at this stage, the prediction process becomes more reliable and consistent. The commented line is instructing you to install TensorFlow version 2.20.0. This sets up the environment so the code that follows will run correctly. Using this specific version helps keep behavior consistent across different systems. It is especially important when the code depends on features or programming interfaces that may change between versions. We start by importing 3 key libraries for our script. First, the JSON library lets us read, parse, and modify data stored in JSON format. Second, the random library provides tools for generating random numbers, which is helpful for setting seeds and making results reproducible. Finally, we import NumPy, a numerical computing library that efficiently handles arrays and supports fast mathematical operations used throughout the code. In this script, we import TensorFlow, a powerful library for building and training machine learning models. Using TensorFlow, we can create a small demonstration model and access tools for defining neural network layers. It also lets us compile the model and run predictions. By importing TensorFlow, we can efficiently construct and manage the entire model within our code. To make our code give the same results every time it runs, we set deterministic seeds for all the random number generators we use. We choose the value 7 for the random library, so its random operations always follow the same sequence. We also set NumPy's random seed to 7, so its generated numbers are reproducible. Finally, we set TensorFlow's random seed to 7, so any randomness in model initialization or training is consistent across runs. This practice is important for reliable debugging and fair comparison of results. This line displays the version of TensorFlow currently in use. It provides a quick check that the intended version of the library is installed and active. Confirming the version helps ensure that the rest of the code will be compatible and run as expected. We define a simple regression model using the Keras interface in TensorFlow as a sequential stack of layers. The model takes input data with 3 features, then passes it to a dense layer with 4 neurons that uses a ReLU activation to learn nonlinear patterns. After that, a final dense layer with 1 neuron and a linear activation produces a single numeric output. This linear output is appropriate for regression tasks because it can take any real value. The model is set up for training using the Atom optimizer, which is chosen for its efficient and adaptive updates to the network's weights. It uses mean squared error as the loss function, which calculates the average of the squared differences between predicted and actual values. This combination defines how the model learns from data and how its performance is evaluated during training. We generate a small synthetic training set as a 2-dimensional array with 5 examples and 3 features using floating point values. The first example contains all zeros to act as a baseline case. The next 3 examples each have a single feature set to 1, while the others remain 0, so the model can learn the effect of each individual feature. The final example has all features set to 1, representing a case where all features are active. Together, these patterns help the model learn basic relationships and interactions between the features. We create a training target array using a numerical library, where each target is a single floating point value placed inside its own small list to match the model's expected input shape. The target values are 0, 1, 1, 1, and 3, and they correspond to the synthetic training examples defined earlier. These values are stored in a float32 format to ensure they work smoothly with TensorFlow operations during training. The model is trained using a fit function that takes the training data and target values as input. Training runs for 50 epochs, meaning the model goes through the entire dataset 50 times to adjust its parameters. The verbose setting is turned off, so no training progress is printed, which keeps the console output clean. This configuration is useful when you want to run experiments quickly without detailed feedback during training. We use a dictionary of expected features to define how each input to the service should be configured. It includes 3 features: age, income, and whether the user is premium. Each feature has a minimum and maximum allowed value. Age ranges from 0 to 120, income from 0 to 1 million, and the premium flag is either 0 or 1. These ranges let the system validate and normalize incoming data before it is used for model predictions. This function normalizes a feature value to prepare it for use in machine learning models. It first clips the value so it stays within a specified minimum and maximum range. If the minimum and maximum are equal, it safely returns 0 to avoid dividing by 0. Otherwise, it subtracts the minimum from the clipped value and divides by the range, scaling the result to lie between 0 and 1. This ensures all inputs share a consistent scale. The function starts by trying to convert a JSON text into a Python dictionary using the standard JSON parsing tool. If the text is not valid JSON, the parser raises a decode error. The function catches this error and instead raises a value error that clearly states the JSON payload format is invalid. This approach ensures that only correctly formatted JSON data is accepted and processed, helping maintain reliable data handling. The code first checks whether the parsed JSON data is a dictionary because the service requires the top-level JSON structure to be an object. If the data is not a dictionary, it raises a value error to signal that the JSON format is invalid. This validation step is important to ensure that all later processing works with the expected data structure and can run reliably. We begin by creating an empty list that will hold the normalized values of each feature from the incoming JSON data. Starting with an empty list lets us add each processed feature value one by one as we loop through the expected features. This step is important because it organizes the data in a consistent structure. Once filled, this list can be easily converted into the format needed for making predictions with the model. For each expected feature, we look up its value in the incoming data, and if it is missing, replace it with a safe default given by that feature's minimum value. We then make sure the value is numeric by converting it to a floating point number, and if this conversion fails, we raise an error because the feature must be numeric. Once we have a valid number, we normalize it to a range from 0 to 1, using its defined minimum and maximum limits. The resulting normalized value is added to a list of features that will be used for later processing. The code takes the list of normalized feature values and converts it into a NumPy array using 32-bit floating point numbers. It then reshapes this array so it has one row and a column for each feature. This prepares the data in the proper format for input into the model. Before making a prediction, the code first checks that the preprocessed input has exactly 3 features, matching what the model expects. If the number of features is not 3, it raises an error stating that the feature length is incorrect. This validation step is important because it ensures the input data is correctly formatted and helps prevent runtime errors during model prediction. The function returns the features as a model-ready tensor that has been reshaped to match the model's expected input format. Because of this reshaping, the data can be fed directly into the model for prediction. This step completes preprocessing by turning the list of normalized features into an efficient format the model can process. We define a wrapper function that takes a JSON payload, converts it into a numeric tensor using a helper so it is in the right format for the model, and then runs the model to get a prediction. Any extra logging during prediction is turned off to keep things simple. The model returns a tensor, so we extract the first value, convert it to a regular Python number, and round it to 3 decimal places. Finally, the function packages this rounded prediction into a response dictionary and returns it for use or display. We create a sample JSON object to simulate a client request, containing 3 fields: age set to 35, income set to 50,000, and is premium set to the word 1. Age and income are simple numeric values, while is premium is stored as a string that may need to be converted to another type later. We then use a JSON library to turn this dictionary into a JSON formatted string so it is ready for further processing in the service layer. The service layer prediction function takes an example JSON request and first preprocesses it into a numeric tensor that the model can use. The model then generates a prediction from this processed input. That prediction is converted into a standard Python floating point number and rounded to 3 decimal places. Finally, this value is placed into a simple response dictionary that holds the prediction result, which is stored in a variable called response. The program first prints the original JSON request, so you can see the raw input data before any processing. It then prints the service response, which shows the prediction result after the input has gone through the model. By comparing these 2 outputs, you can see how the service layer transforms raw input into a cleaned and processed result, illustrating the effect of its preprocessing and prediction steps. This material describes a preprocessing workflow for a TensorFlow regression model that acts like a service layer. A simple model is trained on synthetic data, but the main emphasis is on how input data is prepared before making predictions. A preprocessing function normalizes incoming features according to expected configurations so that values fall within the required ranges. The script accepts input in JSON format, converts it into a model-ready form, applies normalization, and then generates a prediction. Finally, it returns a dictionary with the prediction rounded to 3 decimal places and prints both the original JSON request and the prediction response to show how the data flows through the system. Interpreting model responses. When a client asks for a prediction, the model's raw output must be converted into a clear, structured response before it is useful. This means turning complex internal data into understandable formats, such as labeled categories with confidence scores or readable text. For example, an image classification service might return the top label, its confidence score, and some metadata for each image. This transformation lets clients easily use the predictions without needing to understand how the model works internally. When interpreting model responses, it is important to decide how much information to show and how to present uncertainty. Instead of only giving the single top prediction, a system may provide a ranked list, probabilities, or brief diagnostics. For instance, in medical triage, listing the top few possible conditions with their probabilities makes it clear these are suggestions rather than firm diagnoses. Recommendation systems can similarly show items with relevance scores and short reasons, such as noting that they are similar to what the user viewed. Thoughtful response design like this reduces misinterpretation, supports human oversight, and helps organizations apply their own rules effectively. When working with model responses, it is important to handle edge cases and errors in a clear and transparent way. The system should distinguish between technical issues, such as malformed inputs, and model-related issues like low confidence or out-of-distribution data, and encode these explicitly in its output. For example, a translation service might signal low confidence to invite user clarification, while a fraud detection system might flag anomalies to guide further review. Providing this context makes the model's behavior more understandable and supports safer use in applications where decisions affect the real world.
Serving performance basics. Efficient request batching.
Efficient request batching is crucial for high-performance model serving, especially on GPUs or specialized chips. Instead of processing each request as it arrives, the server briefly waits to group several requests into a single larger batch. This batch is then processed at once, allowing the hardware's parallel computing power to be used much more effectively than with individual requests. For example, a recommendation model handling thousands of requests per second can greatly increase throughput by batching them into groups of tens or hundreds without adding more hardware. When batching requests, you need to balance latency and throughput. Larger batches use hardware more efficiently and allow more requests per second, but they also make each user wait longer. In tasks like fraud detection, fast processing of a full batch is helpful, but waiting too long to fill that batch can delay important decisions. To manage this trade-off, set clear limits on both batch size and how long you wait to form a batch, so requests are handled promptly while still making good use of the hardware. To design an effective batching strategy, you need to study real traffic patterns and see how different batch sizes affect latency and throughput. During busy periods, you can use larger batches because requests arrive quickly without adding delay, while quieter times call for smaller batches to avoid making users wait. Some systems adjust batch sizes automatically based on current load or group requests by model version to improve efficiency. By tracking metrics such as average latency and tail latency, you can tune these settings for stable, efficient performance under changing conditions. Python code. Efficient request batching. This script shows how to efficiently batch requests by comparing the latency of batched and unbatched predictions. It provides a simple way to see how grouping requests together can change response times. By using it, you can better understand the trade-off between latency and throughput when processing predictions. The line with the exclamation mark and the pip install command is meant to install TensorFlow version 2.20.0, ensuring the script uses the correct library version for compatibility and reproducibility. Using a specific version helps avoid problems that can occur when different environments have different library versions. In this case, the line is commented out, which means the installation step is optional or has likely already been done in the environment where the script is running.
We start by importing the time module so we can measure how long operations take,
which is important for evaluating latency. We also import the random module to generate random numbers that serve as synthetic data inputs for our model. In addition, we bring in the statistics module, which is not used in this specific example, but could help compute values like the mean or variance elsewhere in the script. Together, these imports prepare the environment for timing operations and working with generated data. We start by importing TensorFlow, a major library used to build and train machine learning and deep learning models. Importing it gives us access to its tools and functions. We then check which version of TensorFlow is installed, because different versions can have different features or compatibility issues. Knowing the version helps ensure that our code will run correctly and behave as expected. The code uses the random library to set a fixed random seed with the value 42. This means that every time the script runs, it will generate the same sequence of random numbers. Doing this makes the results reproducible, which is important for running experiments and for debugging code reliably. This line displays the version of TensorFlow currently in use, allowing you to quickly confirm that the correct version of the library is installed and active in your script. Checking the version helps ensure that your code is compatible with the library. Since different TensorFlow versions can offer different features or behave in slightly different ways, verifying the version early can prevent unexpected issues later in the program. We define a simple dense neural network using the Keras sequential API that takes input data with 16 features. The first hidden layer has 32 units with a ReLU activation to introduce nonlinearity and learn complex patterns. A second hidden layer with 8 units and ReLU activation further refines these learned relationships. The final output layer has a single unit with a sigmoid activation, producing a value between 0 and 1, suitable for binary classification as a probability. The model is set up for training using the Atom Optimizer, which efficiently and adaptively updates the network's weights. It uses binary cross-entropy as the loss function, which is appropriate for tasks where there are 2 possible output classes. Together, this configuration defines how the model learns from data and how its prediction errors are measured during training. We first create a small batch of dummy input data using TensorFlow's random uniform function, which produces a tensor with 8 rows and 16 columns filled with random values. This synthetic batch is not used for training or evaluation, but simply to run the model once before timing it. By doing this warm-up step, we allow the model to complete any initial setup or compilation, so that later performance measurements are more accurate and not affected by startup overhead. The code first runs a warm-up prediction to initialize the model by sending sample inputs through its prediction function. This is done with verbose output turned off, so it runs silently without showing progress or details. The warm-up step loads needed resources and allows the model to compile internal optimizations. As a result, later predictions can run more smoothly and with lower latency. This function simulates making a single prediction with a machine learning model. It first checks that the input tensor has the correct shape of 1 by 16, matching the model's expected input size, and uses an assertion to catch any mismatch. After confirming the shape, it runs the model to generate a prediction for that single input without producing extra console output. This approach is useful when handling individual predictions, such as in real-time processing, instead of using batch predictions. This function handles predictions for a batch of inputs by first checking that each item has the correct number of features, which is 16. It uses an assertion on the batch tensor's shape to enforce this requirement. If the shape is valid, it calls the model's prediction method on the entire batch. The prediction is run with no extra output, keeping the process silent and efficient. The function sets up a way to measure how long predictions take for a given number of requests based on both the total request count and the batch size. It first creates a collection of random input tensors, each shaped as 1 by 16, using TensorFlow's random uniform generator. This collection is built to match the total number of requests. These synthetic inputs are then used to test and compare prediction latency when requests are processed one at a time versus processed in batches. The code starts by recording the current time with a high-precision timer, which is well-suited for measuring short time intervals. This starting timestamp marks the beginning of the entire scenario. After all requests have been processed, the code will compare the end time to the starting time to find the total processing duration. From this total time, it can then compute the average latency for each request. The code first checks whether the batch size is 1, and if so, it processes each input sample individually in a loop. For every sample, it calls the single sample prediction function, so predictions are made one at a time instead of in a group. This setup mimics a system where each request is handled separately. It is useful for studying how not using batching affects latency and overall performance. When the batch size is greater than 1, we first create an empty list to hold the current batch of samples. As we loop through the input samples, each one is added to this list until its length reaches the desired batch size. At that point, we join the samples along the first axis into a single tensor that represents a full batch, and we pass this tensor to the batch prediction function. After the prediction is done, we clear the list and start collecting the next group of samples. This cycle repeats until all samples have been processed, allowing multiple requests to be handled efficiently at once. At the end of processing, the code checks whether any samples remain in the current batch that have not yet been handled. If there are leftover samples, it combines them into a single, smaller tensor along the first dimension. This smaller batch is then sent to the batch prediction function. By doing this, the system ensures that every request is processed, even if the final group of samples does not form a full batch, so no data is left unprocessed. To find the average latency per request, the code first measures how much time has passed by subtracting the start time from the current time using a high-precision timer. This elapsed time represents the total duration for all requests. It then divides this total time by the number of requests to get the average time per request in seconds. Finally, it multiplies this value by 1,000 to convert it to milliseconds and returns that average latency. In this experiment, we simulate synthetic traffic by sending a total of 64 prediction requests. We then group these requests using different batch sizes of 1, 4, 16, and 32. By changing the batch size, we can compare how processing requests one at a time versus in larger groups affects both latency and throughput. This setup lets us study the trade-offs between faster response times for individual requests and higher overall processing efficiency. We create an empty list to store the results of our latency measurements, then loop over each batch size we want to test. For each batch size, we call a latency measurement function with the total number of requests and the current batch size, which returns the average latency in milliseconds. We convert this average latency to seconds and compute throughput as the number of requests processed per second. We then save the batch size, average latency, and throughput together in the results list. This process lets us see how changing the batch size affects both latency and throughput. The code first prints a header line that labels the columns for batch size, average latency in milliseconds, and requests per second, creating a clear format for the output. It then loops through a list of results where each entry contains a batch size, an average latency, and a throughput value. For each entry, it prints the batch size, the average latency rounded to 3 decimal places, and the requests per second rounded to 1 decimal place. This formatted output makes it easy to compare how different batch sizes affect latency and throughput. This script uses a simple TensorFlow neural network to study how batching affects prediction latency. After warming up the model with an initial prediction, it measures how long it takes to handle a fixed number of requests using different batch sizes. By comparing single predictions to batched predictions, it shows the trade-off between latency and throughput. As batch size grows, the average time per request usually decreases, so more requests can be processed per second. The script reports these results as batch size, average latency, and requests per second to clearly demonstrate how batching can improve performance. Latency and throughput metrics. When deploying a model, 2 key performance measures are latency and throughput. Latency is the time it takes to handle a single request from input to response, including all network and processing delays, and it reflects the experience of one user. Throughput is how many requests the system can process per second, showing how well it serves many users at once. For example, a payment processor's fraud detection model needs low latency to make quick decisions on each transaction and high throughput to handle many transactions during busy periods. When evaluating latency, focus on the full distribution of response times, not just the average. Pay particular attention to the median and higher percentiles, such as the 95th or 99th. This helps show how often users experience slow responses. A system can have an acceptable average latency while still frustrating many users if some requests are much slower, for example, due to resource contention or occasional large inputs. It is also important to measure latency under realistic conditions, including actual network paths and authentication layers, because a service that seems fast inside a data center can be noticeably slower for real users once factors like API gateways and encryption are involved. When evaluating throughput, focus on how the system behaves as you increase the number of concurrent requests and how this affects capacity and latency. In a well-tuned system, throughput rises with more parallel requests until a resource such as CPU or network bandwidth becomes fully used. Beyond that point, extra load leads to higher latency and more errors. To understand these limits, run controlled load tests and track throughput, latency, resource usage, and failure patterns so you can set safe traffic thresholds and configure auto-scaling to protect the user experience, such as for a customer support chatbot during peak demand. Python code, latency, and throughput metrics. This script demonstrates how to measure serving latency and throughput using a very small TensorFlow model and simple dummy requests. Its purpose is to focus on basic timing behavior rather than realistic or complex deployment scenarios. By keeping the model and inputs minimal, it isolates how long requests take to process and how many can be handled over time. This makes it a straightforward tool for exploring performance at a high level without extra deployment details. The commented line is instructing you to install TensorFlow version 2.20.0. This ensures the script uses a specific TensorFlow version so it behaves consistently across different systems. It is a setup step to make sure the required library is correctly installed before running the rest of the code. We start by importing 3 key libraries for our script. The operating system library lets us interact with the system environment, such as setting environment variables. The time library provides tools to measure how long operations take, which we need to calculate latency and throughput. The statistics library offers basic functions like mean and median, which we use to analyze the latency data collected while the script runs. We start by importing TensorFlow, a widely used library for machine learning and deep learning, so we can access its tools in our program. After that, we print the TensorFlow version currently in use. Knowing the exact version helps check compatibility and makes debugging easier, since different versions can behave differently or offer different features. The code first sets a fixed random seed for Python by configuring the hash behavior so that hash-based operations give the same result every time. It then sets TensorFlow's random seed to 0 so that random processes inside TensorFlow, such as initializing neural network weights, are also consistent across runs. Together, these steps make the script's behavior reproducible, allowing you to obtain the same results each time you execute it. We build a small sequential model in TensorFlow's Keras API as a simple feed-forward neural network. It takes input data with 4 features, then passes it through a dense layer with 4 neurons using a ReLU activation to add nonlinearity. The output then goes to a final dense layer with 1 neuron and a linear activation, which is appropriate for regression. This creates a basic neural network structure that can be trained and used for making predictions. The model is set up for training using the Atom Optimizer, which is widely used because it is efficient and adapts well during learning. It uses mean squared error as the loss function, which is standard for regression tasks. This loss measures the average of the squared differences between the model's predictions and the actual target values. Together, these choices define how the model updates its weights and how its performance is evaluated during training. We begin by creating a simple dummy dataset using TensorFlow. First, we generate random input data with 32 samples, each containing 4 features. Then, we compute the labels by summing the 4 features of each sample, using a TensorFlow function that reduces the data along the feature dimension while keeping the result as a single column. This gives us a straightforward input and output pair that can be used to train and evaluate a model. The model is trained using the fit method, which takes the input data and their labels and adjusts the model's parameters. Training runs for 3 epochs, meaning the model goes through the entire dataset 3 times. During this process, the verbose setting is turned off, so no training messages are printed, keeping the console output clear and focused. We generate a single dummy input tensor using TensorFlow's random uniform function with a shape of 1/4, which produces random values that mimic a typical request to the model. This synthetic input stands in for real data and allows us to run the model as if it were handling an actual request. Using this setup, we can accurately measure and test the model's inference time on a standard input size. Before measuring a model's performance, it is helpful to run one initial inference with a dummy request. This warm-up step lets the model complete any setup or optimization it needs. Once this is done, the timing of later inferences will better reflect the model's true performance. In other words, warming up removes the extra overhead of the very first run from your measurements. We use a helper function to measure how long a model takes to run. It creates an empty list for latency values, then repeats a fixed number of test runs. For each run, it records the start time, performs a model inference on a sample input with the model in evaluation mode, and then records the end time. The difference between the end and start times is converted to milliseconds and added to the list. After all runs are complete, the function returns the list of recorded latencies. The code evaluates the model's latency by running it many times with the same sample input. It calls a latency measurement function, giving it the model, one example request, and a setting to run 50 trials. Each run produces a latency value in milliseconds. These values are collected into a list that can be used to analyze how the model performs over repeated executions. The code first finds the median latency from the list of measurements, giving the middle value that is less affected by extreme outliers. It then calculates the mean latency, which is the average of all measurements and reflects the overall typical response time. Together, these two metrics provide a clearer picture of the model's latency performance than either one alone. The code first sorts the latency measurements in ascending order so percentiles can be found correctly. It then computes the index for the 95th percentile as 95% of the list length minus 1, and similarly for the 99th percentile using 99%. Using these indices, it retrieves the corresponding latency values from the sorted list, making sure the index is not negative. The resulting values represent the latency below which 95% and 99% of all measurements fall. To estimate throughput, we divide 1000 by the median latency, which tells us how many requests per second the model can handle. This approach assumes the median latency is greater than 0. In rare edge cases where the median latency is 0 or negative, we instead set the throughput to 0 to avoid invalid division and meaningless results. We report several latency metrics to understand the model's response time. First, we print the median latency in milliseconds, rounded to 4 decimal places, which shows the central value of the latency distribution. We also print the mean latency, similarly rounded, to give the average response time. In addition, we report the 95th and 99th percentile latencies, which indicate the latency values below which 95 and 99% of responses fall. Together, these rounded metrics summarize the model's performance characteristics in terms of latency. This code prints an estimate of how many requests per second a single worker can handle, which is called throughput. It calculates throughput from the median latency, meaning the typical time it takes to process one request. The result is rounded to 2 decimal places for readability. This gives a quick, clear measure of the model's performance in terms of requests processed each second. To simulate batched requests and measure throughput, we first choose a batch size of 16, meaning we handle 16 requests at the same time. We then generate a random tensor with 16 rows and 4 columns using TensorFlow's random uniform function. In this setup, each row represents one request in the batch. This allows us to observe how the model performs when processing multiple requests simultaneously, instead of one at a time. To measure the time for a batched inference, first record the current time using a high-precision performance counter to mark the start. Then run a forward pass of the model on the batched input, while the model is set to inference mode, not training. After the model finishes processing the batch, record the current time again. The difference between these 2 time measurements gives the total duration of the batched inference. To evaluate batched processing, first find the batch latency by subtracting the start time from the end time and converting that duration to milliseconds. This value represents the total time to process the whole batch. Then, get the average latency per request by dividing the batch latency by the number of requests in the batch. Finally, estimate throughput by taking 1000 divided by the batch latency and multiplying by the batch size, which gives the number of requests handled per second. This code reports performance metrics for batched requests. It first prints the total batch latency in milliseconds, which is how long it takes to process the whole batch. It then computes the average latency per request by dividing the batch latency by the number of requests in the batch. Finally, it estimates the throughput in requests per second by dividing the batch size by the batch latency and converting that value to a per-second rate. This script builds and briefly trains a small TensorFlow neural network on dummy data, then uses it to measure latency and throughput. It runs single inferences multiple times to collect timing data and computes statistics such as median, mean, and percentile latencies. Using the median latency, it estimates how many requests per second the model can handle. The script also tests batched inputs to measure how performance changes when processing multiple requests at once. Overall, it reports both single and batched request performance to show how efficiently the model can handle different workloads. Scaling model replicas.
After you have optimized a single model server and its request batching, you may still hit capacity limits.
To handle more traffic, you can run multiple identical instances of the same model and distribute incoming requests across them. This is similar to adding more checkout lanes so more customers can be served at once and wait times go down. An orchestration layer such as Kubernetes or a custom load balancer usually manages these replicas. The key idea is to share the workload across several servers to improve both latency and throughput in real-world use. Adding more replicas mainly increases throughput and can also improve latency under heavy load. With more replicas and a load balancer, the system can handle more requests per second and reduce waiting time during peak traffic. However, this does not make each individual inference faster. It only allows more inferences to run at the same time. You still need to monitor each replica to ensure they all perform well and remain healthy. To scale replicas effectively, you need ongoing measurement and adjustment, rather than simply adding more instances when performance drops. Track how latency and throughput change as you vary the number of replicas, and watch for the point where adding more no longer improves results. This usually means you have hit a shared bottleneck, such as a saturated database or limited network capacity. In practice, a system may scale up during peak times, yet still slow down if its data services cannot keep up. Overall, scaling replicas must be part of a broader strategy that keeps the entire system balanced and responsive under changing loads. In this lecture, you learned to deploy a saved model using TensorFlow Serving or a similar serving stack, expose a prediction API endpoint that accepts JSON inputs and returns model outputs, and evaluate basic performance characteristics of a served model, including latency and throughput. In the next module, Module 10, we will go over advanced topics.
Thank you for your attention. See you all in the next lecture.